In this lesson of the course, we will be dealing with the fracture behavior of GRC. First of all, it should be highlighted that the presence of fibers in the GRC have a capital influence in the material properties of the material. In the case of tensile behavior, the fibers increase the ductility of the material, and also their presence promotes the existence of a branch where a process of multi-cracking takes place. Such multi-cracking process enhances the tensile strength of the material. In the case of the flexural test, the presence of the fibers introduces an even more notorious change. The linear elastic behavior of the material that is given by the presence of the cement mortar changes after the limit of proportionality is reached. Similarly to the case of the tensile behavior, the glass fibers create a multi-cracking process in the material that remarkably enhances the properties of the cement mortar. Not only the ductility is enhanced, but also the tensile strength is improved. However, the tensile and the flexural behavior tests alike have certain drawbacks that should not be overlooked. First of all, the damage mechanisms involved are complex and therefore are not easily analyzed. And finally, the damage that appears in the material in the test is distributed in large regions of the samples. These two factors cause great problems when we desire to obtain the properties of such material. Consequently, a modification of a previously well-known test that are also employed for cementitious material has been planned. Such well-known test has been extensively used for concrete and is similar to that established in RILEM TC 187. However, in the case of GRC, the sample has not a square cross-section. In the case of GRC, using a square section does not represent the usual relations between the thickness and the rest of dimensions of the GRC elements. Consequently, the width and height of the samples differ, being the width much smaller than the thickness. On the contrary, the span between the berries of the samples has been maintained. Similarly, a notch of a third of the height has been performed in the central part of the sample. The dimension of the samples can be seen in the image that appears in the slide. In the left part of the slide, the test setup can be seen. It has to be underlined that placing such a slender sample in vertical position, resting in the cylinders that are used as bearings, has great difficulty. In the right part of the slide, the test results can be seen. It is clear that the behavior of the material was quite stable, showing a limited scattering. It should be highlighted that the maximum crack opening in the case of a usual formulation of GRC reached up to 1.5 mm, which is a usual CMOD value obtained in concrete samples with 100 mm square section, which proves the great ductility of GRC. The only difference among the samples can be found in the maximum load register. If the normal formulation of GRC is modified by adding a 25% of the cement weight by metakaolin, there are several changes in the fracture behavior that should be noticed. First of all, the scattering among the test results is noticeably higher than in the case of the normal formulation. In addition, the maximum crack opening is much greater than in the case of the normal formulation. In this case, the maximum crack opening reaches up to 2.5 mm. And moreover, the major changes have been registered in the unloading part of the curve. That corresponds to the zone where the influence of the glass fibers is greatest. In order to quantify such differences between the formulation and the average behavior of the samples has been obtained. As can be seen in the figures, the presence of metakaolin reduces the stiffness of the material to a third of the control of the formulation that has been used as the control. However, the formulation with metakaolin is 100% more ductile than the normal formulation. Moreover, the maximum load of this formulation is 25% higher than in the normal formulation. The differences in the ductility of the material have been obtained by comparing the energy absorbed during the test in both formulations. This can be performed by comparing the area under the load deflection curves. As can be easily seen, the differences can be noticed by comparing the red and the blue areas. It can be seen that the red area is much larger than the blue one. Divided these areas under the curves by the area of the fracture surfaces generated during the fracture test, the fracture energy of the two formulations can be compared. As can be seen in the table, in the case of the normal GRC formulation, the fracture energy obtained is 455 newtons per meter, while in the case of the formulation with metakaolin is up to 1800 newtons per meter, which represent 4.5 times and 18 times more than the fracture energy of a normal conventional plain concrete. Thanks for your attention.